So in the second part, we're going to do something we're going to prove a theorem about polytopes, which is going to come back and help us to understand designs, okay? So I think this is one of the most beautiful theorems in the theory of polytopes. So I want to do this very carefully, and it's a technique that's going to allow you to find faces of polytopes, okay? So in general, like all the small examples you saw on the board, it's pretty easy to see the faces. But even the examples you saw in Mathematica, the orange and pink ones that were rotating, it's not so easy to see what the faces are. And it'll take you a lot of time to calculate them, okay? You could calculate them, right? Like, you know the vertices. So what would be one sort of very, simple algorithm to find all the facets? Do you see? So every facet is, in 3 dimensions, every facet will be spanned by 3 things, right? There may be more points there, but you just need 3 things to get the supporting hyperplane. So you can take every collection of 3 points, calculate the plane that contains them, the hyperplane, and then you got to check whether this is supporting, meaning you got to check there are no points that are on both sides, no other points, right? But this would require like n choose 3 checks, right, in 3 dimensions. In general, you need n to the power d checks, and it's time consuming, okay? So that is a check. If you needed to, that you could do that. Sometimes it's the only way to do it. But I'm actually going to show you a theorem that's going to, in some cases, it's not always helpful, but in some cases, it's going to be really helpful. So this whole topic is called Gale duality. And it is named after David Gale, who is a game theorist, combinatorialist, many, many things. He's from our time, 20th century. Okay. Okay, so suppose we start with the following. So suppose I start with a polytope P, that is the convex hull of, say, V1 up to Vn, and the polytope is living in Rd. Okay? So, for example, let's do a simple example. I want to do this. So I take a pentagon. Let's make it like that. Okay. And I'm going to give it coordinates. So the coordinates here are 0, 0, 1, 0, and maybe this is 2, 1, this is 0, 1, and this is 1, 3. No, 1, 2. All right? So I want to work with this example, so let's use this. So this is a pentagon, and so these are my endpoints. So this one is V1, this one is V2, this one is V3, this one is V4, and this one is V5, okay? So D for us is, of course, 2 in this example. Good? So here, of course, you see all the facets, right? You immediately see all the facets. But I want to do this very simple thing so that it's easy to check that what we're doing is correct. And then we'll do something that we can't visualize, right? So first, let's do something that we can actually visualize. Okay, so the first step of the algorithm is like this. So we're going to construct a matrix A. Sorry, this is not the adjacency matrix, it's just A, okay? And this matrix is going to have in the top row a row of 1s, as many 1s as there are vertices. There are 5 vertices, so I put 5 1s on top. This is the top row, okay? And then in the columns that are coming under here, we put those vertices down. So the first vertex, so this should be V1, this should be V2, this should be V3, V4, and V5, okay? So this is the general construction. So you put the vertices in the bottom, and a row of 1s on top, okay? So in our example here, the A matrix is going to be, let's construct it. So this is going to have 1, then 0, 0, 1, and then 1, 0, 1, and then 2, 1, 1, and 1, 2, and 1, and 0, 1, okay? So this is a matrix, good? Okay, so let's also assume that this polytope is d-dimensional. So this is, the dimension of my polytope is D. Okay, just makes everything easier to do the math. But if it's not, then it lives in it has its own affine hull, which is not the ambient space. You can make a linear transformation that makes the affine space into a full dimensional Euclidean space and so on. Okay, let's not go there, okay? So this is a full dimensional polytope and we construct this. Okay, so what's the rank of this, what do you think is the rank of this matrix? So this, okay, let's count the number of rows and columns first, right? So each of these VIs is d-dimensional, but I have an extra 1. So that means the number of rows is d plus 1. Agreed? And the number of columns is the number of vertices. So this is d plus 1 by n. Good? Okay, so what have we done when we stick this row of 1s? Do you see what's happened to the polytope? What have we done? We did this yesterday, right? So this is sitting in 2 dimensions. So what we're doing is we're putting it at height 1 in 1 higher dimension, right? That's the geometry of what's happening. So geometrically, we have taken, this is the height, this is maybe the x1, let's call this x0 because this is this extra coordinate. And we have this x, so we had, downstairs the polytope was living here somewhere. This is where the polytope was living. And now we have lifted that polytope into 1 height 1. So up here now the polytope is here. Okay? I won't try to draw it exactly. That's all that we've done. So we haven't changed anything about the combinatorics of the polytope. We've just embedded it in 1 higher dimension. Okay. So then what's happened is that all the points that were here, so let me just do a schematic. So if I had 1 vertex here downstairs, it has now lifted to this point, and this point is 1 comma v, right? That's basically what has happened. I have lifted the v to 1 comma v, okay? And now if I look at I want to calculate the rank of this matrix, okay? So do you see what the rank has to be? Maybe let's do it on this example. What? 3? 3, okay. So 3, the rank of this polytope is 3. You can see this easily from the first part, right? Like from this part, you can see that it's an upper triangular matrix. Its determinant is the product of the diagonal entries. This is not 0, okay? So this is a rank 3 matrix. And in general, you can check, let me leave this as an exercise, that the rank of this matrix by this construction is going to be d plus 1, which is exactly the number of rows. Okay, so D was the dimension we started in, we put this whole row of 1s on top, and now we are going to get something that is D plus 1 dimensional, rank D plus 1, okay? So check this please at home, and it's coming from the fact that the polytope is D-dimensional. That's really what we're using here, okay? Polytope is D-dimensional, so these guys already have rank D, and then the extra ones are not going to mess anything up. So linear algebra exercise, okay? So the rank is D plus 1. So that means the dimension of the kernel, the right null space, should be what? Let's call it, that's the nullity, right? So the nullity, which is the dimension of the right null space, I want the right null space, should be n minus this rank. Do you agree? So it should be n minus D minus 1. Yeah, n minus d plus 1, which is n minus d minus 1. That is the dimension of the null space. Okay, very good. So then the next step is to calculate a basis for the null space. So we're going to, we're going to let's construct a matrix B. So let me put that here. So this is the first thing you got to do. And the second thing we're going to do is to find a matrix B whose columns span the kernel of A. Do you have questions, Divya?
Rank of A is D plus 1 is not clear. It is at least D is known.
Yeah, that's the exercise.
Okay.
Okay. Yeah, it's an exercise. Okay. So it is D plus 1. It's not going to drop to D. So basically, I'm arguing that the all ones is not in the span of the other rows. Okay. So check that. And that comes from the fact that the V part already had rank D and the ones are not in the span. So something, think about it. Okay, at least in the example you believe it, right? Yes. So it is true in general. So let's not go there. So think about that. That's just some linear algebra. Okay. So in part 2, I'm going to calculate a matrix whose columns span the kernel of A. Okay, so what does that mean? So that means so here's my A matrix. The A matrix is 1, 1, 1 up with these V's at the bottom. This is the A part. And now I want to construct a B matrix. So it's going to look like this. This is the B matrix. So that this product is equal to 0. Okay, so the columns here should be spanning the kernel of the A matrix. Is that okay? All right, that's what I want to construct such a B. Yeah? So everybody agreed that if this product is equal to 0, then every column of the B matrix makes 0 inner product with every row of the A matrix. So the columns of B will lie in the kernel in the null space of the A matrix. Is that okay? So I construct, and so what will be the size of this? I just want a basis, not span. Columns form a basis. So I don't want any extra stuff. I just want to form a basis of the kernel of A. Okay? So here there will be some columns. But how many columns do we need? Okay, so first of all, so let's write the size of this matrix. So A was D plus 1 by N, and its rank was D plus 1, so it was full rank. So B has size N, right? Number of rows is N because it has to multiply. And then this part will be, what we calculated exactly, N minus D minus 1. Okay? So there are N minus D minus 1 columns, which is the co-rank of the original matrix, A. That's the number of columns. Okay, so let's do it in our example. Do you see something quickly that lies in the kernel? So here's the matrix in the example. So here I want to construct a matrix whose columns, so how many columns will this have, the B? 2, just 2, right? Because the co-rank of this matrix is 2. There are 5 columns, rank 3. So the kernel has dimension 2. We need to find 2 vectors that span that kernel, okay? So, do you see anything quickly? Perpendicular to all ones, yes. And to the other 2 rows, okay? So it has to sum to 0 because it's perpendicular to the all ones. But we have to think a little bit harder to find one. So for example, let me just start by putting these 2 here. Okay, I can fix some part of the matrix, right? Linear transformation. So I'm going to insist that the last 2 things are 0, 1, 0, 0, 1. So now can you help? So whatever we put here, 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 and here, 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 must sum to minus 1, exactly. In both cases, but it should also dot to 0 with these 2 things. I haven't worked this out, so.
Because you know that it has rank 2.
Yes, I know it has rank 2. So I know I can transform whatever basis I have in the kernel. Yeah. So I'm just fixing something so that my life becomes easier, right? I can always fix one submatrix to be the identity. That's all I'm doing, okay? Can you just try, please, on your paper, see if you see something that'll work? So this is a 2. So let's use the bottom row first, maybe, right? So if you use the bottom row, you get a 2 from these 2 and nothing from here. So then what could we use? Minus 2 here. Okay, if you put minus 2 there, then there has to be a 1 above it. So now from the third one, I have minus 4 plus 1. Can you give me the whole column? So let me erase this. Somebody give me a whole column. It's going to be, it's going to be by construction independent. right? Because I put the identity at the bottom. So whatever you give me, if it works, it's going to be independent. Okay? So we don't have to worry about independence. We just have to make sure that it dots to 0.
So -2, 3, -2.
-2, 3, -2. Okay? Does everybody agree that works? 3 minus 4. Yeah. Yeah, it works. This works, I think. Okay, everybody agrees? Okay, let's find another one.
So actually, this is a nice choice because then you get everything you need.
Okay. We need one more. Sorry, Sam? -2? -1. Okay. This is correct? That's what you said? Okay. So everybody please check. Does it work? Certainly works for the first row, for the second row, 2, -2. Yep, that's okay. -1, 1. Yeah, seems okay, right? All right. So do you see by construction, do you understand that trick to put the identity at the bottom? Because this is a basis, right? This is a basis. So I can always make a transformation that makes the last part of this matrix. So if I had some basis for the kernel, right? If I had some basis, let's call it B prime, I can always transform it with some invertible matrix. I can put an invertible matrix U here. It's still a basis, okay? So I just chose the invertible matrix in such a way that the bottom part is the identity, which you can always do because this is a full rank matrix, okay? That's what I did. Okay, great. So we got the B, all right? So here we got the B. And what I want to do is to write this B in not in terms of the columns, but in terms of the rows, okay? So let's give the name B1, B2 up to Bn to the rows of this matrix. So these are row vectors. These are the rows of the B matrix. Okay, so in our example, we are interested in the rows of this matrix. So -2, -2, 3 -2, 2 -1, 1 0, and 0 1. Okay, so we are going to do that. And now I'm going to make a definition. So definition is that the original A thing gives me, let's take all the columns of A. So the columns of A are this one, 1, 1 0, 1 2 1, 1 1 2, and 1 0 1. We're going to call this the A configuration. It's just the collection of columns of the A matrix. And I'm going to call the collection of rows of the B matrix, but I think of them as columns. So in our example, it's -2 -2 is the first row, then 3 2 is the next row, and -2 -1 is the next row, and then 1 0 and 0 1. Okay? So I get 2 configurations out of this construction. Right? So I'm just sort of telling you a recipe, and we're going to prove why everything works at the end. I haven't even told you why we're doing this. We're just like writing down a recipe. Okay? So again, let me summarize. We have a polytope. Our goal is to find the facets of this polytope. So first step is to construct the matrix A like this with a row of 1s. We argued it has full rank, or you will argue. You then construct the kernel matrix with exactly the right number of columns. That's linear algebra. You can use Mathematica or whatever to find that. And then I'm constructing these 2-point configurations. The first one came from the columns of the A matrix. The second one came from the rows of the B matrix. Okay? So these are called dual configurations. So
just to clarify, A lives in Rn plus 1.
In R, D plus 1.
Sorry, D plus 1.
Yeah.
D lives in Rd.
Let's see. This lives in R D plus 1, and this lives in R n minus D minus 1.
Oh, okay. This is the
Yeah. In general, this is what's happening. Okay? So in general, I have this B configuration. So let's say that. So A is the configuration of all the 1, Bi's, and this lives in Rd plus 1. And B is the configuration of all these Bi's, and this lives in Rn minus D minus 1. Everybody okay? I have these two configurations. Okay. So now, let's take the B configuration and let's actually draw it. All right? So let's draw the B configuration. So this is my R2. It lives in R2. And I want to draw all of those vectors. So I'm going to start with the last two because they're easy. So here is 1, 0. And this is B1. Okay. And then there is 0, 1, which is B2. I don't really need to know the coordinates. I'm just going to index with the numbers, B1, B2. And then there is minus 2. Let's go from the beginning. So minus 2, minus 2. So you have to draw this very correctly to see what's happening. So we'll try. Okay, so this is B1. But this is not B1, sorry. Yeah, this is B4 and this is B5. And that's B1. Okay, so you have to draw them as a vector. Okay. And then we have 3, 2, which is tuck, 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 somewhere here. So this one is B2. Okay. And then we have minus 2, minus 1, minus 2, minus 1. So like here, and that one is B3. Okay, everybody okay? So I drew the dual configuration, the B configuration in the plane, okay? Now, so if this dual configuration is in the plane, you can see it. If it's even 3-dimensional, we can kind of see it, but above that, we can't really see it. So whatever I'm telling you is only really useful when this number is small, when this number n minus d minus 1 is like 2 or 3 or 1 or something like that, okay? Even 4, even 4 maybe you can deal with, but not really after that, okay? So after that, it's not going to be so useful, but it's useful for polytopes where the co-rank of the matrix is small, the A matrix is small. Okay, so now here's the theorem. So this is a theorem. Okay, this is the Gale duality theorem. It says that you can read off the faces of that polytope by looking at this green configuration. That's the point, okay? So the point is that, so let me write the theorem. Theorem says that so let's pick a subset I inside 1 through n. This is the number of vertices in the polytope. Convex hull of Vi for I not in big I is a face. So it's going to identify you faces, okay? So this is a face. So the convex hull of Vi, I not in this index set, is a face of P if and only if 0 lies in the relative interior. I'll explain what this is in a second. So relative interior of the convex hull of the Bi such that I belongs to I. Okay, so that's the theorem, and we're going to now illustrate on this example, and then we will see why this works. Good? Gale. Yeah, these are called dual configurations. So they are dual. So this is sort of dual in the sense of oriented matroids. That's where this whole theory comes from, but we won't really go there. Okay, is the theorem okay? Can you see? Everybody see? Okay, so let's do some checks. So let's pick a face of that polytope, okay? Oh yeah, so for now just think of it as interior. Relative interior means that if your collection of vectors that you're looking at have a lower affine hull than the ambient space, then you got to think of interior in that affine hull, not interior in space, right? So for example, if I have this paper lying on the table and this space is the ambient space, then this point, if I put my finger in the middle of this paper, that's not the paper doesn't have an interior, right? This white convex set doesn't have an interior in the ambient space. But it does have an interior if you only look at the affine span of the paper. That's all it means, okay? So take your collection of things, convexify it, and then in that space, if you take the affine span of that convexification, in that affine space, if it has an interior, and there you have to check whether 0 is in there. That's all relative interior means. So relative to the set that you're working with. Okay, so let's check if it works, okay? So can we pick a face over here? Let's pick a face you like. Which one do we want? So I have to number these. This was one, oh, we already numbered them. This was V1, V2, V3, V4, V5, okay? So let's pick a face. So for example, maybe we pick this face. Okay, that's a face. And this face, I'm going to just to be very simple, I'm going to write this as the face 2, 3, okay? That means it's the convex hull of V2 and V3. I'm just going to record the indices of the vertices that I need. Good? Okay, so this is the face 2, 3. And this theorem is saying that something is if the convex hull of Vi such that I doesn't lie in an index set is a face, then something else has to happen, okay? So what do you think should be this big I for the face that we just picked? So that face is the convex hull of V2 and V3, okay? So I should be the other stuff, right? So in our example, the I should be, so in the red example, I is the complement of the numbers you see there. So it is 1 and 4 and 5. This is I. Got it? So I pick a face, I write down the indices of the vertices that are in that face, and I should be the complement according to this theorem, okay? So the claim is that then the theorem we should be able to see that 0 lies in the convex hull of B1, B4, and B5, okay? So let's check B1, B4, B5. So here is B1, B4, and B5, okay? So the convex hull of these guys is this, right? And indeed 0 lies in the interior of that convex hull. Is that okay? Everybody okay? All right. So we checked one direction. I picked a face, I looked at its indices, the I is the complementary indices, and then I saw that 0 lies in the relative interior of the convex hull of the B's that come from the I, okay? Let's go backwards. Can you pick something that is, so I'll leave the red the way it is, let's use yellow. Can you pick another set that has 0 in the relative interior of its convex hull?
No, B2, B3, B4.
Yeah, B2, B3, B5 will not work, for example, right? Because if you convexify it, it's probably on one side of the origin.
No, B2, B4, B5.
B2, B4, B5. Yeah, that also won't work. Okay, let's check that one actually. So Arun's saying take B2, B4, and B5, these ones, okay? So if I convexify those, I will get this, which definitely doesn't have 0 in it. So the yellow I is 2, 4, and 5, okay? So the complement, I bar, is equal to 1 and 3, okay? So what happens to 1 and 3 in this picture? Yeah, it's definitely not a face. It's this, okay? It's not a face, all right? So the yellow and the red are positive and negative results. And so we can check another one if you like. Let's pick one more that actually gives us a face.
Thanks to your labeling,
Yeah,
if you just avoid consecutive things,
that's true.
then
Yeah, if you avoid consecutive things, that works. Okay, is the theorem fairly clear that this is going to happen? Okay, so this is called Gale duality. Okay, so if I can draw this picture in 2 dimensions, so for example, I could have a polytope with 100 vertices living in 98 dimensional space. This Gale dual picture will be 2-dimensional, okay, or whatever it is, n minus d minus 1, 1-dimensional. So maybe I should go to 97 vertices in 100-dimensional space. The other way. Okay, so whatever. You can have a lot of vertices in a high-dimensional space, but if n minus d minus 1 is small, 2-dimensional, 3-dimensional, 1-dimensional, you can read off all the faces of that polytope without actually being able to visualize it. Okay, so in homework you have to do a 4-dimensional polytope, which you certainly cannot see. So we will go there. Okay, so is the theorem clear? Everybody got this?
Statement of the theorem that smallness of n minus d minus 1 is not.
It's not there.
For practical purposes.
Exactly. And this technique was used to disprove many conjectures in polytope theory. So for example, there was a conjecture, it was unknown whether you can realize every polytope. So polytopes can be just told to you combinatorially, right? You can just say, these form a phase, these form a phase, these form a phase. You can just give a collection of indices like the way I wrote it here. I can denote this whole polytope by saying this is 2, 3 is a facet, 1, 2 is a facet, 3, 4 is a facet, without actually giving you a picture. I can just give you the combinatorial data, and then you have to realize the polytope. You can draw polytopes that realize that data. And of course, there are infinitely many polytopes that will have 1, 2 a phase, 2, 3 a phase, 3, 4 a phase, right? Instead of this pentagon, I could draw any pentagon. It would work, right? So then there was a question whether you can realize every combinatorial polytope, like with combinatorial data, with rational coordinates, with rational vertices, okay? And this is not true. This is not possible. And the way to prove that it's not possible is to do Gale duality. It's done through Gale duality. So this book of Ziegler's that Arvind showed you in the morning, that has many examples of Gale duality being the tool to disprove like really hard theorems, like hard statements like this, right? It's very counterintuitive, and I think that polytope is even in somewhat small dimension, that you just cannot realize that combinatorics with rational data. You need, I forget it, it's in Ziegler's book, but it's like either 4-dimensional or 3-dimensional. I think it's like 4-dimensional.
You say you cannot realize what is.
You cannot find rational vertices with rational coordinates that gives you, whose convex hull has the combinatorics that I just prescribed. Okay? And you cannot do other things, like you cannot prescribe a face and then complete the polytope. Like you cannot say the face should have this kind of shape or embedding and then finish the rest. There are all kinds of things like this that are like really interesting statements that you can disprove. Most of the bad examples start in dimension 4 and above. So dimension 4 is kind of the threshold for most counterexamples. Dimension 3 is actually very nice. So in dimension 3 you have like Steinitz theorem, Steinitz theorem, that says that if you take the graph of a polytope that's in 3 dimensions, it's always a planar graph. If and only if, okay? So you can draw that graph in a way that the edges don't cross. So there are many special properties for 3-dimensional. 2-dimensional, of course, is kind of trivial, but 4 dimensions is where things start to get really interesting. Okay, so this is Gale duality. Everybody okay? This is the theorem. Okay, so we can do many more examples. So there's one in your homework, in the exercises that you can do. If I have time, I will do one more. But let's actually kind of prove the theorem, and then we'll come back and do more exercises. So let's see, 4, 5, 6, 7. Oh yeah, I need this 7, 8. Okay, let's try this. Okay, any questions on the statement? It's all right? Okay. So first of all, let me write down a lemma that we will prove later, or you can prove an exercise, but I want you to at least check it on the examples. So lemma says that, so we're going to use this notation, okay? I'm going to denote faces, facets, whatever, faces, just with a bunch of numbers. That tells you which vertices or which points that we originally had among the V1 through Vn, which of those actually lie on that face, okay? Now, it doesn't all have to be vertices. There could have been another vertex, like another point V right there. So for example, if this was a V6, then this face would have been 2, 3, 6. Even though the 2 and the 3 are the only ones that are necessary, you want to record all of the numbers corresponding to the points that live on that face, okay? That's really important. And if, for example, if I had a point here and this is V7, this would not get recorded in any proper face, right? It doesn't lie in any proper face, and we never care about the whole polytope, right? So just be careful about that. Okay, so that's where this notation is coming from. So J in N is a face of P if and only if the convex hull of the Vj's such that J is not in J intersect the affine hull of the Vj's such that J is in J is equal to the empty set. Okay, we'll see it in a picture in a second. So we'll prove this later, but let's at least just see what's happening. Okay, so maybe we check it on the 2, 3 face again, okay? So it's saying that if 2, 3 is a face, so J is 2, 3, then the convex hull of the Vj's that are not in 2, 3. So let's take the convex hull of the things that are not 2, 3. So that is 1 and 4 and 5, right? These guys. So let's take their convex hull. So maybe I make it green. So the convex hull of the things that are not in the face is this. Do you agree? So this is the convex hull of the Vj's that are not in J. J is 2, 3 for me right now. Okay, so J is 2, 3. So I'm convexifying the Vj's that are not in J, and then I'm intersecting it with the Vj's that are in J, but it's affine hull. Okay? So the things that are in J is this red piece, that's the face. If I take its affine hull, what happens? So if I take its affine hull, I need to like just extend that segment forever, right? So I extend the segment like this. This is the affine hull of the face F. Okay, so affine hull, if you like to think about, at least the way I like to think about affine hull is you take a collection of points, you draw all lines through every pair of points, and any new points you construct, you also draw lines through every 2 of them, and then you'll get the whole space, right? So in this example, there's only 2 points that we have to worry about, so the affine hull is this line, okay? So notice that this convex hull and this affine hull don't intersect, right? That's what this is saying. So something is a face if and only if the convex hull of the complementary things does not intersect the affine hull of that thing, okay? Let's do another type of example where you take something that's not a face. Let's take something that's not a face. So maybe this guy. Can you see this color?
Yeah.
More
Okay.
dimension and it's 5, it is 5 face. So it is easy like 6 or 7 face. Then we can get to different area so that the intersection is 5.
But if it's a yeah.
2 dimensions, it's not good.
No.
So what are you worried about?
C6 maybe. It's C5. For graphical I am saying it's C5. Like 5. I am saying to draw C6 kind of.
You want to draw a cycle with 6, okay, and?
Then we can get some 2 area such that their intersection is 5. Then the contradiction part we can understand better.
Okay. Okay, I'm not fully sure. Let me finish this. We'll come back to it, okay? So I'm just taking something that's not a face. Do you agree? The purple thing is not a face, okay? So if I take its affine hull, I just get this. This is the affine hull, okay? And if you convexify the rest of the stuff, you will get this, this, and this. This is the convex hull of the rest. And you see that the affine hull and the convex hull will intersect, okay? So if you have a face, it kind of stays away from the rest. This makes sense, right? Because Arun told us that there's a supporting hyperplane on a face. So the face is on the supporting hyperplane and everything else is not touching this hyperplane, okay? So the supporting hyperplane, the affine hull is not exactly the supporting hyperplane, but you can see that there is a separation, right? So the face is on a hyperplane and everything else is far away from that hyperplane. So if I convexify that stuff, it won't intersect this thing. Whereas if you cut through the middle of the polytope and you convexify what's left, it's going to have stuff on one side and the other side, so the convex hull will intersect. Is this okay? Is this clear, Aditi, or do you want more example? Is okay? All right.
I want to see an example where this affine thing is coming.
Okay. You want a higher dimensional example?
No, maybe a non-face where the convex part is intersecting itself, right?
Yeah. What do you mean the convex part is?
Even if you take the convex hull of the...
So what do you want J to be?
Yeah, pick a J that you like.
That's what I'm looking for. Here, V4 and V2,
Uh-huh.
you take just the convex hull.
Oh, yeah.
And the straight line, right?
The convex hull of V2 and V4 is just this line segment.
That itself is intersecting.
That itself is intersecting.
Why that affine thing is coming?
Why do you need the
The
affine?
other case, the red one, even after extending it, it is not intersecting.
Yeah, it's an even stronger statement, right? That the affine hull doesn't intersect the... Yeah, it's true. That therefore the convex hull also doesn't intersect. It's an implication, that's true. But what I'm claiming here is even stronger, right? Even if you extend that convex hull, it won't intersect. Good? But what you said is true. It's an implication of the statement.
Does it happen in the two dimension that affine hull may intersect and convex hull?
That's what I was asking.
No, in two dimensions.
Affine hull?
That possibility.
No, she's saying a fine hull will intersect, but,
for example, if you
but convex hull will not intersect.
Does it ever actually happen?
No, it can't.
can't.
It can't, right?
No, but if you take, to start with, if you take a non-convex
No,
polygon,
Yeah, but we're
Yeah,
not
yeah.
taking-
No, nothing non-convex at all.
then this will make more sense, I think, because then you understand. Because here after extension,
Oh,
you
okay.
extend some side, it will.
Yeah, you're right. So she's saying that if you are, yeah, okay, got it. Okay, let's move on from the lemma. If you got the lemma, let's actually prove the theorem because that's going to take us a little bit of time. But everybody got the picture of this, what the lemma is saying? Okay, so let's actually prove the theorem and then maybe you can think about how to prove the lemma. How would you prove that lemma? While I'm erasing. So you could try contradiction. What happens if you tried contradiction? Suppose the affine hull and the convex hull did intersect and the thing was a face. Then you would get a point that you can write as a convex combination of some things and as an affine combination of some things, okay? And from that you should get a contradiction. That's the idea, okay? But we'll come back to it if we have time today. But let me actually prove the theorem. Yeah, theorem. So it's a very simple proof. So I'm going to prove that theorem. Okay. So let's pick J is a face, if and only if this. Okay. So I'm going to start by picking something that is not a face, and I'm going to show that 0 doesn't lie in the relative interior, okay? So we'll do that direction. So suppose J in N is not a face. Okay? Right. Then by this lemma, we know that if you take the affine hull of the things in J, it'll intersect the convex hull of the stuff that's not in J, right? So let's use the lemma. So then the lemma says, so the lemma implies that the affine hull of the Vj such that J is in J intersect the convex hull of the Vj's such that J is not in J. This intersection is not the empty set. Do you agree? I'm picking something that's not a face. So if I make its affine hull, it's going to intersect the other stuff because the other stuff is on both sides. Okay? So it's going to do that. So let's pick something from this intersection. It's not the empty set, so there must be something in here, right? So in this intersection, then let's pick something called Z from that intersection. So it's not 0. So that means I can write this Z both as an affine combination from this part and as a convex combination from that part, right? It's in the intersection, therefore you can write it in both ways. Okay, let's first write it as a convex combination. So I'm going to write this as some QK VK. I'm using the convex part where K is not in J. And then this is a convex combination, so I must also have QK, sum of the QKs is 1, and I must also have QK is greater equal to 0. All right, so I'm expressing that Z is in the convex hull of the Vj's where J is not in J. So this is the way I can write Z. Yeah, QKs are multipliers. So I have Z is QK VK sum, where K is outside of big J, sum of the multipliers is 1, and the QKs are non-negative. Good? But this is also equal to something in the affine span of the Vj's where J is in J, right? So let's also write it like that. So I can also write it as PK VK, where K now lies in J, okay? And now the only condition on the multipliers is that this sums to 1. That's the only condition, right? Because being in the affine span means I have to sum to 1. Yeah? Everybody okay? All right. So this piece is coming from this part, and this piece is coming from that part.
You don't even need summing to 1. You just need that it belongs to that span. Why do you need summing to 1?
That's the definition of affine span, right? So it's like, think of a line, like if I have 2 points, and I want the line through it.
Yeah, any point far away, you cannot write it as sigma, where the sum is 1.
Yeah, with a plus and minus you can. There's no non-negativity.
Okay, so there's just some kind of normalization.
Yeah, there's no non-negativity, but I can write it like this, okay? Yeah, it's a type of, yeah, so this is my definition of affine span right now. This is an affine combination, this is convex combination. Okay, very good. So we have these two things. So now I'm going to subtract this expression from that expression, okay? So let's subtract the second sum from the first sum. So this implies that I can write, if I subtract the two, I will get sum of QK, QK VK. Let me just write it like this. So I think you understand what I'm trying to say. So I'm going to write RK VK, where K now includes everything, okay? And this, because the two sums are equal, I will get 0, where RK is going to be equal to QK if K is not in J, and is equal to minus PK if K is in J. So all I did was I subtracted the second sum from the first sum, okay? And there's no interaction among the VKs, right? Because one sum is over complement of J, the other one is over J. So when I subtract, I will get some new coefficients, which I call RK, which will give sum to 0, but they are just these. They are QKs if K was outside J, and they are minus PKs if K is inside J. Yeah? Good. Okay. What else do we know about what do we know about the sum of the RKs? Yeah, sum of the RKs is 0, right? Because the PK sum is 1 and the QK sum is 1. So when I subtract, I will get this. Okay, so the RKs all sum to 0. All right. And we also have, if K is not, okay, let's stop there. That's enough. Okay. So we have these two properties. So then do you recognize this RKs? Do you recognize where it is from our A configuration, B configuration? Oh, I don't want to erase the theorem. Okay, I already did, so we'll put it back later. Okay, so let's look at this bit that we just got. Okay? So let's think of this. So the sum of the RKs is 0. Okay? RK VK is also 0. This is over all K. This is K in N.
Oh, okay.
So do you see where the R vector lies?
Is that because B?
Yeah, it's in the kernel of A, right? So this implies, so basically the thing that I just did is showing us that 1, 1, 1, 1, 1, V1 through Vn times R is equal to 0. That's what this is showing us, right? Because this piece is exactly saying that the dot product of the all ones with the R is 0. And this piece is saying that the combination of all the VKs with RK is also 0. Do you agree? So this R vector lies in the kernel of the A matrix. Okay? So what we get is that the R vector lies in the kernel of the A matrix. Are we good with this? Okay. Now remember that the kernel of the A matrix is spanned by the columns of B. Right? That's how we constructed B. So this is spanned by the columns of the B matrix. Right? That's how we constructed the B matrix. So R lies in the kernel of A, which is the span of the columns of the B matrix. So can you write R in terms of B? So this means R is equal to B. So B is like a long matrix. I want a combination of its columns to become R. Right? R lies in the column span of the B matrix. So yeah, it's B times something. So let's call it T. Okay? So because R lies in the kernel of the B matrix, it looks like this. Yeah? Good. We're almost done. So now I'm going to unwrap this a little bit. So remember the B matrix had rows B1, B2, in general BK, all the way up to Bn transpose, right? This is the columns, the rows of the B matrix. So I'm just going to highlight the rows now. Yeah? The columns, we didn't name the columns. We only named the rows, okay? So it's B times T because it's in the column space of B. But now I want to like look at the rows. I highlighted the rows and this expression is just this expression, okay? So this tells you, so then we can exactly figure out what RK is, right? The kth element of R. So this kth element of R is going to be BK transpose T. Yeah? So it's this little B vector, the row vector, times T. T is something, T is fixed. Like when I give you R, you can uniquely solve for T, right? Because we only have a basis for the null space. Oh, you okay?
Yeah.
Okay. So we have this, and this is true for all K from 1 to N. Okay, so RK is this, okay? All right, now I'm going to draw a picture. Let's draw the hyperplane whose normal is T. Okay, so T is unique. Does everybody agree with that? Yes. Right? Because the columns of the B matrix is a basis. So there's only one way to write R as BT. Okay, so T is unique. So I'm drawing the hyperplane whose normal is T. Okay? All right, so now let's look at a few more things. So some other things I know is that, remember these QKs are non-negative, right? And some of the RKs are QKs, right? So what we know from there is that RK is greater equal to 0 if K is not in J. Okay, so it's greater equal to 0 when k is not in J. So that means these bk transpose t's are also, so this is exactly bk transpose t. Okay, so bk transpose t's are non-negative when k is not in J, right? So how can I draw those bk's in my picture? I just want to draw the bk's where k is not in J. Okay, here's my hyperplane with normal t.
So it makes acute angle.
Yeah, it has to make acute angles. So all those bk's are going to look like this. Maybe one of them even lies on this hyperplane. That's okay. Okay? So this is how all the bk's where k is not in J will look like. Okay? So those bk's all look like that. Okay? Can all of them lie on that hyperplane? So could it be that all those red things I drew are actually on the hyperplane perpendicular to t?
It's sum to 1.
Yeah, because you can't, because the qk's, which are the same as the rk's, sum to 1. Okay? So, so it must be, so since the sum of the rk's for k not in J is equal to 1, it implies that there exists some Rk, which is Bk transpose T, that is positive. Okay? There must be something positive because the Rk's have to sum to 1. So it cannot be that all the Bk transpose T's are 0, which is the only way that the Bk's can lie on the hyperplane, right? To lie on the hyperplane means that Bk transpose T must be 0. But all of them can't be 0 because they are exactly those qk's and they have to sum to 1. So at least one of them must stick out like this, like my picture. Okay? Now what happens? Do you see, here's the origin. Okay? So if you convexify these bk's that don't lie that where k is not in J, will 0 be in the relative interior of the convex hull? So let's convexify, so I'm going to convexify these bk's, okay? So if I convexify them, I will get something like this. I will get this. So at least one of them sticks out. The rest may all be on the floor, okay? So this is, the floor is our hyperplane normal to T. Let's say a bunch of them are on the floor, but one of them sticks out. And then I convexify the whole thing. Where will 0 lie? On the boundary, right? It has to be on the boundary. There's no way, the only way I can put 0 in the convex hull of this is if there was something either, okay, it could be that there was another, there could even have been another bk like this, and maybe I also needed to include that. So I could have included that too, and then I get this whole thing up here as the convex hull. That's the best I can do, right? So either they're all on the floor and some of them are sticking out, definitely something is sticking out. So if I convexify it, 0 goes on the boundary, right? If everything was on the floor, then 0 would be in the relative interior, right? So it's really important that something stuck out, right? So something stuck out, so then 0 goes on the boundary, okay? So that's the proof. So what we just argued is that, so what we got is that 0, so all of that implies that 0 is not in the relative interior of the convex hull of the VJs such that convex hull of the BKs, of the BKs such that K is not in J. Okay? So if I start with a non-face, I will get that the complementary B's do not contain 0 in the relative interior of the convex hull. And it's an if and only if, you can trace everything backwards. So that's the end of the proof. Okay. I want to try to do a bigger example so that we can do something you cannot see. But is there a question on the proof?
So why does does this fail if I take improper phase? It should go.
Oh, empty set and the other one?
Yeah.
I think you can. It doesn't fail, I don't think.
But it will fail, right? Because if I take.
I don't know. I don't know about the improper things. The empty set is the only thing we can. J is a phase. Okay.
I mean, if I take.
Yeah, I think it works for everything, but let's see. Oh, this is the lemma.
So if I look at the theorem, I take I to be everything, 1 through n.
Yeah.
Then convex hull of everything is a phase, right, with P itself.
Yeah.
But
And then the complement is
empty.
empty, but I think
Zero does not belong to that.
so I think the convex hull of the empty set is
The origin.
maybe the origin by definition. Okay, so that's left to the mathematicians, the corner cases, but works for most of them, right? Yes, so please check. So we can look in Ziegler's book what the exact statement is, but I think it is exactly this. Okay, so I erased the theorem, so let me put back the theorem because I wanted to try to do an example in the remaining time. So this is lemma. Can I erase the lemma? So this you can try to prove on your own, right? It's the same kind of argument. Pick, if the intersection is not empty, then pick something in the intersection. You can write it this way and that way. You should get a contradiction. Okay, that's the idea. So the lemma maybe we don't need, but let's write the theorem. Again. Okay, so let me give you an example to work on while I'm writing the theorem here. Actually, so do you want one that you can see or not see? No opinion? Okay, if you have no opinion, then maybe I will leave the one you cannot see to you. Let's do the octahedron. So I want to convexify. So P is the convex hull. This is the octahedron. Okay, so the points are, so I'm going to number them like this, 1, 2, 3, 4, 5, and 6. And these are just plus minus the unit vectors. Okay, so this is, where are all the colors? Yeah, this is E1, this is minus E1, this is E2, and this is minus E2, and that's E3 and minus E3. Okay, so this is the convex hull of 1, 0, 0, that's the first one, minus 1, 0, 0, that's the second one, 0, 1, 0, that's the third one, 0, minus 1, 0, fourth one, 0, 0, 1, 0, 0, minus 1. So this is V1, V2, V3, V4, V5, V6. And we write the A matrix. Let's do it. 1, 2, 3, 4, 5, 6. And then here I have 1, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, minus 1. So this is A. Okay? And then how many things will be in B? So this is also a rank 4 matrix with 6 columns. So it should be 2 things in the thing, right? So let me just give it to you and see if you can actually draw the Gale dual. So you have to be very careful that you number these things exactly in this order. Okay, so if you change the numbering, everything will go wrong. So this is B1, this is B2, this is B3, and so on. Okay, so you have to keep the numbering here in the same order as the numbering here. Okay, so please try the Gale dual while I write the theorem back and see if we can recognize the faces of the octahedron. Oh, I didn't give you I did give you a B. This is B.
B1 is equal to B2.
Yes, so you have to double number it. Okay, so B1 is the same as B2. That's fine. We allowed repetitions. So you would want to put, yeah, these are all doubled up, right? So this is B1. So this is 1 and also 2.
3, 4, and 5.
Yeah, so some people put a double arrow to note that there are two things there. This is B1 and B2. And then this is B5 and B6. And then you have to finish, right? There's another double one. So you should be able to read off all 8 facets from this picture. But the picture is not complete. Mine is not complete. Does it work out? Many possibilities. So let's start reading off the things that have 0 in the convex hull, right? So what all can we do? Let's start reading them off.
1, 3, 5.
Yeah, you can do 1, 3, and 5, okay? 1, 3, 5, 1, 4, 5, great. And then 1, 1, 4, what did you say? Let's do it. 2, okay. Yeah, okay, let's put it here. 2, 3, 4, 2, 4, 5, 2, 4, 6, 2, 3, 6. Okay, so can you check that the complements are facets there? They're actually facets, not even faces, right? So 1, 3, 4. Let's do 1, 3, 4. 1, 3, 5? Oh. Okay, is this correct? I just wrote down what? 1, 3, 5. 2, 3, 5. Okay, so let's do this one that's circled. So if I take 1, 3, 5, then 0 is definitely in the convex hull. So then I have to look at the complement, which is 2, 4, 6. Okay, so I have to look at 2, 4, 6. 2.
No, that numbering is not that.
Oh yeah, this one, right? The white one, okay. So we have to look at 2 and 4 and 6. Okay, so agreed, that's a facet, that's this back facet over here. Okay, that's a back facet. Can you pick out an edge from there? So let's take an edge, like maybe this edge.
Take 4 times.
Yeah, so I only have 4 and 1. Okay, So the face that I'm interested in is just 1 and 4.
2, 3, 5, 6.
Yeah, exactly. So the complement is 2, 3, 5, 6. And is that okay? 0 in the relative interior of the convex hull? Yeah, it's good. So if I want an edge, I have to pick up more things from the B side, right? So how do we figure out what the facets are? Do you see immediately from that side what we got to do to only get the facets? You choose the minimal number of things that have 0 in the relative interior, okay? So the minimal number of things will correspond to facets. Minimal things in the green side, the B side, will give you facets, the biggest things on this side, and the biggest things on the green side will give you the smallest things on this side, the white side.
That's why we do it.
Yeah, so it's a duality, okay? And it's this nice connection that helps you read off faces of polytopes from just a low-dimensional configuration. So it's super, super helpful. And in the afternoon, we'll see that this is going to help us organize all the designs that we saw yesterday, okay? So this theorem will tell you, so remember yesterday we discussed that, I'll put back again what design was, but we saw that it's actually hard to compute it because you have to get the sparsest vector that satisfies some conditions, and that's hard. And so, you know, in a computer, we would just do one norm minimization, we would get something roughly good. But today in the afternoon, we'll see that all of the minimal designs actually live on the facets of a polytope. And so you can actually find them all through this trick of Gale duality. Okay? But Gale duality is independently interesting. There's like a whole chapter in Ziegler's book about Gale duality and all these amazing statements that were disproved using this technique. Okay? You can't prescribe a face and finish the polytope. You can't embed the polytope with rational coordinates. I mean, there exists examples of polytopes whose combinatorics can be specified, but you cannot realize the polytope in space with rational coordinates. Things like that. Okay? Lots of other results too. There's all kinds of counterexamples that were found with this technique. So this technique is from the 60s, 1960s. It's not like terribly old. But it's very, very powerful. Okay, so maybe we can stop there. Okay, we'll come back after lunch.
Any questions?
Yeah, if you have questions, please ask. You can also think about the lemma. I don't think I put it in the exercises, but maybe you can adopt it as an exercise. So think about how to prove that lemma. The Gale duality proof was not so hard, right? Do you agree? Disagree?
One way is the other way is
It's the same. You just go backwards. It's the same. Yeah. So you can just, I mean, it's basically, we're using all these definitions of what is a convex hull, what is an affine hull, and then just doing some linear algebra and some geometry, right? We did some geometry.